So I remember to mark attendance. Thank you. Okay, so last week we stopped over at this lecture. We have some very general, just very quick recap. We talked about the different types of memory. Yeah, so some analogy and how the disk arm and also the head spins in order to get the correct sector, the correct track, and also the right block to do to access the data from. And I think we stopped right about here about the disk mapping. So we have table, we have record, we have values. We made a few assumptions. So namely that no record is larger than a block. So meaning that all the records are able to fit into a single block. So we call that a block is a single so-called you retrieve so-called data from at least a single block at least. So no record is larger than a block, and each record is entirely contained in a single block. So which means that there is no chance that something like this block one, let's say this record one and this record two. So there is no chance that something like this will occur. Yeah. So this is the assumption that that we will have. So let's look at this example. So assuming that these 88 records, or rather assuming that there are 88 records over there. So let's assume that every single attribute here has a certain size. So it is assuming that every single record is 64 bytes. How do we get this 64 bytes? We are assuming that, okay, SID is, let's say this is 8 bytes. Over here, this 16, 8, 8, 8, and 16. All together, we sum them all up, so it's 64. So assuming that each record is 64 bytes, and one block is 512. So 512 divided by 64, and I take the lower bound. So I think this is going to be 8. Yeah. So that's how I get 8 records that is able to be stored in a single block. Okay. So let's look at the next slide. There are various ways that the data can be stored onto disk. So this is the first way. We have a fixed length record. So each record is fixed in length. So meaning that each record, regardless, I'm going to allocate a certain number of bytes to that every single record. There may be issues whereby I mentioned earlier of records crossing boundaries, and the so-called the solution is that if there is empty space at the end of a block, this will be allowed to be unused. So this is the solution. So this will allow us, or rather this will ensure that our records, they will never cross boundary. It's something that we want to avoid happening. Mainly because we want to avoid the situation whereby at any point of time we may need to retrieve 2 blocks in order to read a single record. That is the situation that we want to avoid. Okay, so this is the first thing. The second thing is the following. the first problem, and this is how we solve it. The second problem is what happens if we delete a record? How then do we record down that the record is being deleted? So this is how we do it. So let's say that we have this as the original table with all the populated records. We will need to have one additional so-called row, which is known as the header, or you can call it like a pointer. And this would then start to point to all the records that have been deleted. So in this instance, record 1 was deleted away, record 4 was deleted away, record 6 was deleted away. So what will happen is that this pointer will start to point to all the empty records so that we will be able to, so if let's say another record gets deleted away, what happens is that this then will start to point to here, and this will be the resultant, how the resultant table would then look like. Oh, this slide is not posted, is it? Oh, I'm sorry, yeah. Yes, I will post this slide. I didn't know that it's not posted. Okay, I'll post it on later after during the break. I'll post it there. Yeah, sorry about it. Yeah, I wasn't aware. Yeah, so this is how the fixed length record is done. Okay. The second way of doing it is the variable length record. In the variable length record, you are allowed to store multiple record types in a single file. So this allows variable lengths for one or more fields. So for example, you may have a variable character, which is allowed for so-called variable lengths. And so it's easier for you to keep note of this kind of records. And it allows repeating fields such as arrays. So how do we then do this? So let's explore this now. This is an example. So let's look at what this is. So typically we have a block. Okay, sorry. So the first thing we have is we want to store the number of entries there are in a single block. So in this, we have multiple records in a single block. Okay, so before that, so we have multiple records in a single block, and what we have is that firstly, we store the number of entries that are in the single block, and we point it in a way to the end of the so-called the free space. Okay, so this is the number of entries, and we point it to the end of the free space. And thereafter, each of these will be one record, so-called a pointer to one record. And this will then start to point to record 1. The second one then start to point to record 2. The third one will then start to point to record 3 and record 4. So subsequently, each of these pointer would then start to point to their individual record, rather the start of their respective records. So this is how it is being stored in the block. So of course, if I have another one, then I will start to point to here. Yeah. So so this is how it is being stored in the block. Okay. I should have talked about this earlier, but I somehow I missed this part. So let's look at this part now. Okay. So here it tells me that there is a combination of both the fixed and my variable length, so-called, rather in this record, it has both the fixed and variable length attributes. So in this instance, I'm saying that this is fixed and this is being stored over here as my fixed record. Okay, I have three attributes that are of variable lengths. So this, and this, they're all of variable lengths, and they are stored as a how to say, they're stored, they're just stored as required. I mean, because they're variable lengths, so so they are just stored. We don't know how much memory they will take, so they are just stored as per required. In this example, right, they are stored from 21 to 26. And then Srinivasan is stored from 26 to, or rather 21 to 25, 26 to 35, and 36 to 44. Okay. So this is how they are being stored. There is a null bitmap here that separates between my fixed part and my variable part. Okay, so there is this null bitmap between my fixed and my variable. My variable are just stored as per required because it's variable, so we don't really know, like, but in this case, we know the numbers are here. So now we will then, but we also need to find a way to store this. So what we will do is we will store these indexes at the beginning of my record. At the beginning of the record, we will have, so for example, if we have three attributes that are variable, so we then will have three indexes here. In each of these three indexes, we will then store the the starts of my variable attribute and the length that it goes for. So in this variable attribute, it starts from so in this case 21, and it goes for 5 bytes. In my second, it starts from 26. It goes for 10 bytes. So that's why 26 and 10. And in my last one, it starts at 36. It goes on for 10 bytes as well. So this is how a record is being stored in a variable length record setting. Okay. Yeah, I hope this is clear. So this is how the one single record is being stored, and below is how various records are being stored in a single block. I hope this is clear. So let's look at this slide. So the header at the block tells us the number of entries, and records are stored from the end of the block. So we start from the end of the block. Records that are deleted, they are shifted down. If you delete the record, you shift it down. Delete the record, we shift it down. So typically, a block is about 4 to 8 KB. So the cost of doing so is not too expensive. This is the assumption. Okay. Yeah, I hope this is clear. So we covered two types of records. One is the fixed length record, and the other one is the variable length record. Okay. So the other one we want to talk about is record organization in the file. So there are 4 types. So we'll just go through each type one by one. So in the heap file organization, the record can be placed anywhere in the file where there's space. So yeah, so this is the heap file organization. So there's no ordering of records. So typically there's a single file for each relation. There's a sequential file organization. Excuse me. This will be something that we will be discussing more about in the next few slides. There's also a hashing file organization, whereby you compute the hash function out of some particular attribute within the record. And the result of it will then specify the block of the file where the record should be placed in. And of course, there is lastly, there's the multi-table clustering file organization, where related records are stored together so that the I/O is fetches records that are very similar. So the assumption is that if I'm going to if I'm going to do a query, right, I will probably be querying data that is very, very similar, and so that's the motivation. I will discuss more on these four 2 to 3 types later on in the slides. The first is the sequential file organization. So in the sequential file organization, you design it to in a certain sorted order based on the key. So let's assume that the key in this particular scenario is my ID. So in this particular scenario, the ID is my key. So that is why you see that my entire table is sorted according to my key. So you see the pointer at the end of each record points to the next record in the sorted order. So you can tell here, probably these records are all inserted in, and then suddenly this Verdi is inserted in, and so this pointer here points to Verdi, and then Verdi points back to the next person, L Said. Okay, so let's assume that I am now inserting a person with 77777, and no, his name is James Bond. So what is going to happen is that Mr. Quick will not be pointing anymore to Mr. Brett, but he will point to Mr. James or Mr. Bond, and Mr. Bond will then point to Mr. Brett. Okay, so this is how the sequential file organization will be. So of course, as time passes, right, what this is trying to say is that you delete, insert, delete, insert, delete, insert. So so over time, these pointers, although they point to the right place, but in the physical sense, in the physical location sense, they may be very, very far away. And so you may want to do a reorganization in order to put them in physically in the same so-called location once again. It is very similar to so-called your defragment operation. Okay, so the frequency by which reorganizations are required, of course, depends on how often you insert and also how often you delete as well. This point I missed a little bit earlier is this key in this scenario we use ID, but it is not necessarily all the case to be ID. It really depends on the scenario. So it need not be a primary key or even super. It can be anything. It can be name. It can be this. It can be anything. Anything depending on the table. Okay. Let's go on to the next slide. Okay. So this is the multi-table clustering file organization. So what this means is that it will store records of more than one relation on a single table. Yeah. So in this scenario, what we see is that this is storing records from both, let me see, computer science, Taylor, and 100,000. And then you see that physics, Watson, okay, you see, this one is taken from this. And this is taken from this. But how about this? You see, how about this? 101 Sri Vinasan is actually taken from here. And cats is taken from here. And bread is taken from here. So you realize that right now, in this particular scenario, we are storing records of two tables in sort of like a single block. And these three records are particularly chosen because they all belong to the computer science department, computer science department, yeah. And this Mr. Gold is taken from the physics department. So this, in a way, is a very good, rather maybe a very quick query if I want to select everything from a certain department. If I want to select all the, yeah, so if I have, let's say I want to select ID, name, salary, building, budget, everything from department equals to computer science, it is probably going to give me a very quick, how to say, a very quick, a faster, the so-called the records will be written faster because physically they are all stored together in a single block. Yeah. So yeah. So basically, this is what this table, how this table is being arranged in. Okay. So you can, in a way, consider like this storage of record to be very similar to this, kind of, to this kind of query. Just that we are some of the, in a way, you can say that this is the duplicated record. It's not being stored, so they are just stored from this table over here and inserted here. Okay, I hope you can understand what this table is trying to say. Okay, okay. So this is hashing. As you know, hashing is hashing is hashing lah. So you hash the record, it goes into the bucket, and then you just you just throw it into the bucket lah. You just throw the record into the bucket lah. So that's this is the definition of hashing. So in this case, what probably is happening is that we are hashing based on this attribute, and so so-called records of the same attribute gets pushed into the same bucket. Okay, which sometimes may make sense, in the sense because right, if let's say it is very common for me to query something based on, for instance, the county name, then I am going to, then they are physically stored in so-called the same bucket, or even like in similar buckets, and so the query from them will then be faster and more efficient. Okay, let's look at the next slide. Okay, so consider the deletion of record 5. So there are a few ways that we can do this. So let's say that I want to delete record 5. So what excuse me, what are the merits of doing that? So one of the ways we can solve this is that this moves here, this moves here, this moves here, this moves here, this moves here. This is the first way. What the first way is doing. Yeah, sorry, yeah. Okay, so the second way of doing is that if I delete off record 5, record 10 moves over here. So this is the second way of doing it. The third way of doing it is I just, as I said earlier, have a header, and then I just mark, I mark record 5 as deleted. Okay, so these are three ways of doing it now. So actually, this is more of a theoretical discussion. So of course, the first one is the most so-called expensive because you need to shift individual records down. So if you ask me, the first one definitely not something that I would like. Yeah, because I in fact I see no merit in choosing between A versus B, because both of them they maintain the same outcome, in a way the same outcome, but of course this seems to be slightly more expensive than this one. So yeah, so I see no merit if faced with a scenario between A and B. Between B and C, um, I'm both seems to be okay. I think the challenge with this is that we may find that there may be, how to say, if there are multiple records that are being deleted all the time, and multiple or rather common insertions and deletions, the pointers may end up to be very sparse. Yeah, so if there are deletions that are very often, right, so may end up to have like that lah. So you are going to have a block that is very sparsely populated, and that's something that we maybe not so good. Whereas if we have this scenario, we will still have it to be packed, and this is free space. Okay, so this is one of the discussion items that I can think of for the pros and cons between these two scenarios. Yeah. So if you have more, you can let me know. Yeah, I'd be happy to hear them. But I can think of this as one of the potential demerits of this kind of this way of deletion. Okay, let's look at the following as exercise. So okay, insert this, delete record 2, insert this. So okay, so there are a few ways that we can do the insertion. In this scenario, we are going to insert, or in this course, we are going to insert on the last record, last empty record, last. Okay, so in our course, we are going to insert based on the last empty record. So if let's say this is what is occurring, so this will be 2, 4, 5, 5, 6, turn, and 9, 8, and this will be gone, and this will go to brown. If I delete off record 2, okay. So in this scenario, if I were to delete off record 2, so there are few ways that can be done. One way is this points to this, but actually to me, I think that is very complicated. So I would recommend that we do this. Point to empty. And then finally, if I do an insertion of Thomson, this will be 3, 4, 5. Yeah. So you understand the Thomson, and I'm using 6, 7. And now go back to this person. Okay. So this is how this will be like. Okay, let's okay, any questions on this? Yeah, good. Okay, let's go on to the next slide. Okay, so right now we are talking about index. So in index, this is talking about 2 indexes, and this is the master file. So this is slightly easier to understand. For index 1, there's only one, because it's IDR, it's a primary key. So there's only one pointer pointing to each record. So this is slightly easier to understand. In index 2, the index field is has multiple records to it. So what will happen is that the pointer will then point to individual records. Like in this scenario, computer department name has index built on it, and so it will then store in the index file. It will then store multiple pointers, each pointing to the computer science, the record that has the department name of computer science. Okay. Okay, let's go on to the next slide. Okay, so right now we have this. We go back to this example. This was the example we said earlier. So in each recall that in the earlier part we said that each record is 64 bytes. One block is 512 bytes, and we can store 8 blocks, 8 records in a block. If let's say we have 88 records, we means that because 8 records in a block, excuse me, we need 11 blocks. So, and they are not sorted. They are not sorted. So, they can be anywhere. So if we want to do any search of any individual record, we need to search all 11 blocks, which definitely is not efficient. So to reduce time, we use an index in order to reduce the time we use to search for the data. So let's look at what are the index types. So we have 3 types or 2 types. So we have ordered indices based on the sorted order of the values, or we do a hash. So hash indices are based on the uniform distribution of values across the range of buckets. And the bucket to which the value is assigned is determined by the hash function. So we typically use these factors to evaluate how good or how bad your index is. So some of the factors are the access types, the type of access that is supported efficiently. So the access time, how long does it take to find a particular data item or range of items? Like for example, right, we have so let's say a greater than 1,000. You see, I think I will cover this a little bit, excuse me, a little bit later, but hash indices cannot do this well because every single value is a unique hash. So hash indices actually perform very badly in queries like this. Yeah. So we also have insertion time, how long it takes to insert a new data item, deletion time, how long it takes to delete the data item, the space overhead. I talked a little bit about this earlier, which is like how much empty space is there in your data if you were to store it. Yeah. So typically, let's say we want your data to be too sparsely populated as well. So this is an example of how we create an index. In this, we sort of okay, in this scenario, the primary key is automatically being generated from, or rather, an index is automatically being built on the primary key. Okay, so in this particular example, we are using the index to uniquely identify the particular record. Okay, so this is this is it. So we have okay. So this is where index is built directly on the primary key. Okay, so this is one scenario. Okay. So we also have something called the primary index and the secondary index. Okay. So a clustering index is an index where the search key also defines the sequential order of the master file. It's called the primary index. Okay. Okay, so this one can get a little bit confusing. Primary key, right, is primary key. Index is index. Okay. All this, right, has nothing to do with primary index or secondary index. Okay. So this one, right, is a little bit confusing. So you don't, when we talk about primary index or secondary index, right, it is you don't try to think of primary key right now. Yeah, because I can build a primary index not on my primary key. So yeah, so that's that. So the primary index or the secondary index, right, is only depends on the sequential order of my records. Okay, so if my index is built on my record that has a sequential order of it being stored in my physical disk, right, then it is a primary index, regardless of it is whether a primary key or not. Okay, so this one is very confusing, I know. Yeah, but this is something that I will repeat later on again. Okay, a secondary index is if it is not stored physically in a sequential order, then it will be known as a secondary index. Okay. It may be clearer with an example. Okay, so this is the example. Okay, this is the example. Okay, okay. In this scenario, my records. Let's assume that my records here are stored one after the other in this manner. Okay. And in this scenario, if I were to build a primary index on my ID, or rather, if I were to build an index on my ID, because it is stored in a sequential order, the index built on my ID will be a primary index. Okay. Okay, let's look at this scenario. If I were to build an index on this, it will be a secondary index because it is not stored in a sequential order. Okay. If let's say I change this to look like this, you know, com science. So I don't write the rest. It is implicit. So let's say I have another table that looks like this. Right now, if I build an index on my ID, okay, let's now I build an index on my ID. This will now be a secondary index because the data is not stored continuously in sequential order on my disk. If based on this data, I build an index on my department name, this index will now be a primary index because it is stored in a sequential order on my master file. Okay. Okay. So the time is 9:13. Let's take a 10 minutes break while you try to digest this. It's a bit confusing because right now you have primary index, then you suddenly have secondary index and then primary key. So these three terms, right, sometimes very confusing. So I give you some time to digest this. Let's come back at 9:24. Thank you. Hello, welcome back. So before the break, remember before the break, we talked about something quite confusing, which is primary index and secondary index. So remember, primary index has nothing to do with primary key. Okay, it only has something to do with the arrangement of the records in your data. Okay, let's look at this example. So this is the data. Let's say that ID is the primary key. And this department. And you are building an index on this. Is this considered a primary index or secondary index? What do you guys think? This will be considered to be a primary index. Because this is arranged sequentially, and index, as long as the records are arranged sequentially in the physical sense, it will be considered to be a primary index. If you were to build an index on ID, this will be a secondary index, although it is built on the primary key. Okay? So this is something that you may want to get. At first, it sounds a little bit strange, but yeah, just remember that it's like that one. Okay, so let's look at a few ways to describe indexes. This is known as a dense index. In the dense index, the index entry appears for every single search key value in the file. So in this, This is the ID. I have an index built on the ID. This is my primary index. And in this index, every single value there's a search key. There's a so-called pointer. Okay. This is known as the dense clustering index. So notice that I'm building an index on biology. This is also going to be a primary index. So it first points to biology, and computer science points to the first instance of computer science. Electrical engineering points to the first instance of electrical engineering. So it is implicit that all the way here is computer science. All the way here is finance. This is history. This is physics. Okay. So it's a clustering index. It's a dense clustering index because all the items close together are clustered together. The next kind of index is the dense non-clustering index. This is something that I think I pointed out a little bit earlier, whereby every single record has a pointer. This points to this, this points to this, this points to this. So 9 here. Yeah. Okay. So now the question I ask you is this. For a dense non-clustering index, can we rather, if let's say, right, this is let's say look at this table. This is department. Okay. Typically, for a dense non-clustering index, do we use it on a primary index or secondary index? I believe you are meaning to say, although I don't hear it, but I really believe that you are meaning to say that this is typically done on a secondary index. Because if you have a primary index, then you probably want to use a dense clustering index. Let's say you have a primary index on my department. You will probably just use, rather, it is slightly better to just use the dense clustering index to for this. But if you have a secondary index, there's no on department, there's actually no way you can do a dense clustering index on this table. And so you would have to do a dense non-clustering index on this table. Let's look at the another which is the sparse index. So in the sparse index, okay, I ask you a question. Do you think this is done on a primary index or a secondary index? On the sparse index, it can only be done on a primary index because you need the sequential order of your records in order to do the search. And also index then becomes useless. So it means that if I'm looking for record 58583, I will look for this record, I'll get this pointer down, and then I will search down. So this scenario can only occur and will only be correct if my records are arranged in a sequential order, and this will only occur in a primary index. Okay. Okay. Now let's look at the next slide. So how is data stored onto the disk? So we go back again to our recurring example. So in this example, we initially we have 88 records, and we said that we need 11 blocks. To reduce time, we use an index. Let's say that we build an index on SID. SID, we know as 2 bytes. The pointer has 2 bytes. So the size of one so-called index is 4 bytes. For this SID is the pointer. And I have 88 records. So all my indexes will cost me 88 times 4, 2, 3, 32, 352, which is less than 512. So now my entire index can fit into one single block. And this means that anytime I do a search, I just need to search for one block. I get the pointer value, and I go to that block to extract out the record. Later on during the course, either probably on Thursday, we will then go through details of how the time that is required to extract records from the disk. Okay. So this is for this slide. What happens if the number of indexes become too big? So we then create a multi-level index. So we create an index on the index. So let's assume that this is initially my first index. If this index becomes too big, I build an index on this index. And so what I mean to say is, if I were to rotate this in a clockwise fashion, so let's say this is like that, this is like that, this is like that, like that. So it then becomes a tree. So 1, 2, 3, 4, 5. So this 1, 5, 1, 5. So notice that this then becomes a tree. Okay. So I'm going to do a little bit of recap on what a tree is. So we of course, you're very familiar with the binary search tree. So so this is like the root node. Anything less than this gets thrown to the left. Anything right of this gets thrown to the right. So so this is the binary search tree. So the height of the tree is log n. Yeah. So this is just some details of BST. In the M-way tree, the number of records in a node is limited by the value m. So this is what the M-way tree looks like. At any single node, it is similar to a node in a BST. Things that are smaller than the node gets thrown to the left. Things that are larger gets thrown to the right. And there will be cases whereby I have multiple values in a single tree, and this in a way improves the way the records are being so-called accessed. We have the B tree, which is we see on the left over here. In the B tree, we have the root node, and similar to MA tree, root node internal nodes and the leaf nodes. In the M-way tree, or rather in the B plus tree, we have at the leaf, we have the pointers pointing also to the next corresponding sibling in my tree. Okay. The B plus tree has a particular property called the balance property, which ensures that there is good performance in lookup, insertion, and deletion, and which is why it is being used in this context. So the root node, this is a requirement, can hold fewer than n divided by 2 number of pointers, but it must hold at least 2 pointers. A non-leaf node, all these are leaves right now. A non-leaf node must hold, can hold up to n pointers and must hold at least n divided by 2 seeding number of pointers. And the leaf node and hold n-1 nodes and can contain at least n-2, n-1 by 2 seeding values. Okay. Okay. So this is just some theory. Let's look at how queries on B plus tree works. Okay. So assuming that we have the B plus tree over here, we have the root node, we have internal nodes, we have the leaf nodes. Okay, so I'm going to select everything from my instructor where my name is equals to this gentleman over here, and the name is in this scenario and given the index. Okay, the name is the index, and they are stored in this manner whereby everything on the left is less than m, everything on the right is greater than s. Okay. So what is going to happen is that this is the index. In this particular scenario, this is a secondary index because it is not arranged in the alphabetical form on this. So what we do is the root node is already in the memory. So actually this example is quite simple. So the root node is already in memory. So it will search through the root node and you'll find that, oh, this is the pointer that it should be looking at. So it will load this internal node. In this scenario, this internal node points to this record over here, and it finds that, oh, this is record is greater than or equals to my search key. And in this particular scenario, this is empty already. So it will go to this pointer. It goes to my next. Over here, it finds that it is greater than or equals to this, but it is smaller than this. And so it matches my leaf. It goes to it goes to this pointer over here, and it goes down to Srinivasan. Okay, which is where the record is located at. Okay, so only the root node, only the leaf node has the records pointing to my actual physical table. Any questions on this? Let's look at this example of Mozart. We look at Mozart. If I were to search for Mozart, Mozart is greater than or equals to Mozart. This will come to here. Mozart is less than Srinivasan. So this will go directly to this record. You will find that there's a match is less than greater than Mozart, less than this. There's a match on this record, and immediately it goes to the Mozart record here. Okay. I will proceed on. So the query cost in practice is the following. So assume that each node is made to be the same size as the disk block. And the size of the node is equals to the block divided by the size of a page. And in this scenario, we have 4K to be the size of the node. The size of the search key in this scenario, we put it to be 12 bytes. The size of the disk pointer, we take it to be 8 bytes. So right now, we are going to say that what is equals to my value of n. We have 100 million search keys. Sorry, this one should be log of 100. Like this. So we are saying that we have 100 million search keys. And if I have 100, if n is equals to 100 over here, this will be 100 million, log 100 million, base 100. And this will be equals to the value of 4 nodes. Okay. Let me see if I made a mistake here. Okay, let's let me check this. The search of key. Yeah, let me confirm this again with you. But I'm quite sure that my n is equals to 100 over here. I'll confirm this later on again. Sorry, thank you. Okay, let's look at this example. Hash index. So is hash index a primary index or a secondary index? What do you guys think? Oh, yeah. So Hongzi wants me to repeat this explanation, but I think I tell you what. Let me think through to see whether did I mess up in this example or not. Then I'll repeat that later on. Thank you. Sorry about it. Okay. Let's go on with the hash index first. Is the hash index a primary index or a secondary index? So in this, what we have is that for every single value here, we are hashing it and we are storing into a particular bucket. We're hashing it, storing in a particular bucket. So in this instance, what is happening is that our hashes, they are not in a sequential form. And so this is a secondary index. Okay, so this is a non-ordered hashing. So let's compare between the first form of index versus the second form of index. So in the first form of index, we are it is so-called in ordered form, and so we are able to get queries such as this, whereas in the second form, in the first form, we are able to get queries such as this, whereas in the hashing form, we can't, because every single index is mapped to a certain hash, and so it is not in a sequential form. And so hashing is not able to support queries such as this. Okay, okay. Now I have so-called a practice question for you. In general, is it possible to have two clustering indices on the same relation for different search keys? So in general, it's possible to. Do you mind thinking through this while I check on my previous example? So I'll give you maybe about 3 minutes to think through this. I'm going to check on my previous example on that. So go to your slides and just take about 3 minutes to think through this. I'm going to check on this example. Thank you. Mm. sorry. Okay, sorry. Okay, let's go back to this. Let me think through that question for a while first. Okay, so let's look at this question. Is it possible to have two clustering indices on the same relation for different search keys? What do you guys think? In general, it is not possible. So why is it so? So let's say that in general, I have okay, let's look at what the clustering index looks like first. Okay, the clustering index looks like this. Okay, so this is what the clustering index. Let me. This the clustering index. Yeah, this is what the clustering index looks like, whereby this points to 1, and then after that it points to the first one, points to the second one. So if let's say I want to have two clustering index on the same search key, what it means that I have this clustering index here, and then I will have, let's say, another index, another clustering index like that. Something in this line, which means that the order of this occurring must be also sequential according to the order of this occurring. This is very unlikely to happen yes, Brian. It is very unlikely to happen. So that's why in general, you probably won't be able to build two clustering indexes on the same table. Two dense clustering indexes on 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 the same relation for different search trees. So in general, not very possible. Okay, so this is how we answer this question. Okay, let's look at the second one. Yeah, so this one is slightly easier. So find records with the search key value of 11. So firstly, you come to the roots. This is less than this value. So you go to this pointer, comes over here. 11 is greater than equals to this. It goes to this value, comes over here. So over here, we search that, okay, there is a match 11 here, and it will return the pointer. Okay, so this is for 11, 7, and 17. So for 7, quite similar. It goes to this pointer, over here, this pointer, this over here, this pointer. And 17 here, this pointer over here. So it will return values from here all the way to here. Do you think this is primary or secondary? This is probably a primary index. It is probably a primary index because if I can return the start pointer and the end pointer, then probably this is and I can sort of search all the values in between, then probably this is a primary index. Okay. Okay. So this is it. Okay. So okay. For that question, right? Sorry. So for this question, give me some time to think through it tonight. And I forgot how I solved this the last time. This question, then give me some time to think about it. Sorry about it, but give me some time to think about it. How did I solve this the last time? Okay, let me go on to the next lecture. So we have 10 more minutes. Let's make the best use of this. Okay, so query processing. So this is where we start to find out how quick or how fast the query works. So this is the workflow that we have. Don't need to go here first. Okay. We now look at the cost of query evaluation. The cost of query evaluation will be depends on the disk access, which will depend on the number of block transfers, the time it takes to transfer a block, the number of disk seeks, and the time it takes to access a block. So in terms of the disk access, we will then, if let's say you are going to take B blocks and S number of access, you need B times T plus S times, rather B times T and S times TS. Okay, so this is the time that it takes for you to transfer the blocks of data over. Okay. The rest we don't need to go there today. Let's just focus on this single bit. Okay. Once again, we have this recap because it is easy to get confused, but because we just went through this, so I don't repeat again. But remember, the primary index is where your data is stored in a sequential manner. So this is something that we also talked about earlier. So ID is the candidate key, index is considered to be a primary index. Okay, so let's look at the first one, a selection operation, whereby I'm going to do a linear search. So there's no index at all. I need to do a linear search of my entire file. So I will then search, and I find that those records that fulfill my condition will then be returned. So every single block will have to be searched out, and then we will then see if the condition meets that or not. The cost of this operation is going to be a single access, seek access, plus the time it takes to transfer all the blocks over. So why is that so? It's because we are going to, and this is typical the case also, whereby I have all of these blocks that belong to that relation. I take T of S to find out the start of my first block. And this accounts for this first part. And for every single block that is being transferred, it takes me T of T time. So if let's say I have BR number of blocks, the time for me to transfer every block out is going to be this times T of T. So in total, I will need T of S plus BR times T of T. This would be the amount of time it takes me to transfer out all my data out to do a linear scan. Can? Yeah, so this is how we look at this. So linear scan, yeah, it tests. So this is what I was trying to say. So the first is the time it takes to seek my first plot, and then after that is the time it takes for me to select all the rest of my plots. Okay, now I have now an index. Okay, so that the earlier one was the scenario but I don't have an index. Okay, so now I have an index. I have index, and right now I'm trying to say that I have a primary B plus 3 index, and I want to do an equality on my candidate key. Okay. So okay, I will repeat this in the next lecture again, but right now I have index, primary index, equality on my candidate key. Okay. So how do we calculate what is the cost of this? Okay. We will look at this from the tree point of view. That is, so we don't look at that. This will be repeated later, but we look at it from a tree point of view. It's slightly easier. From the tree point of view, let's assume that the height of this is going to be h of I. Okay. For every so-called level of the tree, it always takes me the same amount of disk seek time and my disk transfer time, which is why this only appears one time for every level. But height, this has several levels, and so for every level, this same cost occurs, and so this will be height multiplied by my disk seek plus my disk access time, which is here. So this is just the height of the cost for my so-called the height of my tree. I also need to account for my disk access time and my seek time and my leaf node. And because this is the equality of my candidate key, so how many records will be returned? Number of records that will be returned is only going to be 1, because at most 1, because it's equality on candidate key, means either you have it or you don't have it. And if you have it, only one of this will be returned. So there's no way that you can return 2 records. And so you are only going to go down this thing just one time and one time only. Okay. 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 So if we look at the next record, we are going to have other things, equality on non-candidate keys, and the how to say, the way that we are going to the cost of that will be different. So I don't think I want to go into that this evening. I think this is a good place to stop. And next Thursday, on Thursday, I will do a recap on this again. And I'll also find out what was the what I missed out in the example. Thank you for your patience. Oh, no need, no need. Actually, the formulas you just understand can already. it is all derivable. It's you understand one, right? You understand all already. The height of this, right, is always the same. And how this, and there are going to be different combination of equality of candidate key, primary tree index, secondary tree index, equality or non-candidate key. So there are multiple combinations actually on this. So if let's say I go down this, right, there are actually multiple combinations, but you just need to understand understand how these combinations come about. Then you will be able to derive them quite easily. So have I stopped recording yet? Okay, I'll stop recording now.